Okay, since it's 3 o'clock, I'm going to start. So today we are going to review the notion of valuations and norms. These norms are also sometimes called absolute values. So let's start with recalling that on the additive group R, you have the natural order structure, right? On R, you have the order and it's an additive group. The order is such that it's invariant under translation, which just means that if A is less than B, then A plus C is less than B plus C for all C, right? So from this ordered group, I get an ordered monoid, R union plus infinity. So I just choose some element which I call plus infinity. I adjoin it to the group R, and I extend the addition on the group R to this new set. So of course, elements of R are going to be added as they were earlier. And how do you add plus infinity to an element in X in R union plus infinity? I mean, you just define it to be plus infinity. For every X in R union plus infinity, you define X plus infinity to be plus infinity, okay? So in this definition, you have the only element in this set such that X plus Z is equal to Z for all X is the element plus infinity. Not only do you extend the law of composition, you also extend the order to this new set. So you declare X to be less than plus infinity for every X in this set, okay? So now we have got an addition on this, oh, it should be R union plus infinity. We've got an addition on this, and we have also got an order. It's an additive ordered monoid in the sense that it's associative and unital. Of course, the same unit is namely 0 continues to be a unit for this thing. And these two structures are compatible in the sense that translation by any element preserves the order. If X is less than Y, then A plus X is less than A plus Y for all A in R union plus infinity. Okay, so this is just a fancy way of saying things which you already know. Let's come to the real stuff today. So the first definition is going to be that of a valuation on a field. So you've got a field K, and a valuation V on K is just a morphism from K to this group, this additive monoid which I have introduced, R union plus infinity. And this K here is to be thought of as a multiplicative monoid. So it's a morphism for multiplication. It just means, it just means that you have to have this and this. V of X times Y is V of X plus V of Y, and V of 0 is plus infinity. It transforms multiplication in the field into addition of real numbers and plus infinity. So that's just one of the properties that this valuation V is supposed to have. The important property is this one. What it does to a sum. The valuation of a sum X plus Y should always be bigger than the smaller of the two valuations, V of X, V of Y. Now, I cannot overemphasize the importance of this concept. It might look very simple, but it's a very basic concept in all of mathematics. as basic as what a group is. So what is a valuation on a field? It is just a map V from K to R union infinity, which takes multiplication to addition, which takes 0 to plus infinity, which takes this, the valuation of a sum is bigger than the smaller of the two, the valuations of the two summands. Okay. So, of course, a valuation is also determined by its restriction to K star, because the valuation of 0 is always plus infinity, and the restriction to K star is a homomorphism of groups, of the multiplicative group K star into the additive group R of real numbers. Okay. So that's what, and a valued field is just a field with a valuation. So I should have mentioned here that we have already come across examples. So this VP on K equal to QP, that was a valuation, and VT on the field K, which is K power series T, where little k is any field. In our case, it was a finite field, but that didn't have any importance. The same definition works for any field. So these are some basic examples of valuations. Okay. Why is it called absolute value here? It should be called valuation. The absolute value is a different concept, which we'll come to later. So of course, there's always this trivial valuation, which takes every non-zero element to 0, and which takes 0 to plus infinity, of course. So it's equivalent to say that the image of K under this map V is just consists of 0 and plus infinity. That valuation is always there on every field, and it's called the trivial valuation. It's of no interest, but it just as a trivial group, it doesn't have much of an interest, but still we need to consider it as a group, right? So this trivial valuation is also a valuation. And I'll call a valuation essential if it is not trivial. These are just words. An essential valuation is, people tend to say non-trivial, but I don't like that terminology. Essential is better. Now, here is an important concept, which is that of a discrete valuation. Now, you will notice that if V is a valuation, then V of K star is a subgroup of R, of the additive group R. V of K star is a subgroup. If that subgroup happens to be a discrete subgroup, then I call the valuation to be a discrete valuation, right? There's nothing which forces a valuation to be discrete. The trivial valuation is, of course, discrete, because the subgroup consisting just of the 0 element is, of course, a discrete subgroup. But we know all discrete subgroups of R, right? A subgroup H of R is discrete if and only if either H is equal to 0, or it is a set of all multiples of some strictly positive element, which is uniquely determined by H. This is something that you should probably work out as an exercise if you have not already come across this. The only discrete subgroups of the group R of real numbers are the trivial subgroup and the multiples of some strictly positive real number. For example, this real number A could be 1, in which case the subgroup is Z, which is a discrete subgroup of R. So a discrete valuation, meaning one for which the image of K star is as a discrete subgroup of R, it's going to be called normalized if that image is actually equal to Z. Every discrete subgroup of R is isomorphic to Z, apart from the trivial subgroup. And if the image is exactly equal to Z, we call it a normalized discrete valuation. So for example, these two, VP and VT, these are normalized, they're normalized discrete valuations, right? Because VP of QP star is equal to Z, and VT of K star here is also equal to Z. Okay, right. Now, if I have a discrete valuation which is not trivial, then I have this notion of a uniformizer. What is that? It's an element of K star such that V of that element is the positive generator of Vk star. Why does Vk star have a unique positive generator? That's because Vk star is a discrete subgroup, is A dot Z, I should say. What did I say here? Yeah, A dot Z. Yeah, so it is A times Z for a unique A, which is strictly positive, and anything which has valuation equal to A is going to be called a uniformizer. So if V is a normalized discrete valuation, then a uniformizer means, what does a uniformizer for such a situation mean? Means an element of K such that V of an element, let's give it a name, an element pi, such that V of pi is equal to 1. Because 1 is the unique positive generator of the group Z. That's the value group when you have a normalized discrete valuation. So this V of K star is sometimes called the value group of the valuation. So V is a, if V is a valuation, then of course you get this subgroup V of K star, which is a subgroup of R, and it's called, sometimes called the value group of V, right? Okay, so one of the first things that you can prove is that if zeta is an element of K star of this multiplicative group, which is finite order, which means that zeta to the n is equal to 1 for some n. That's what it means for it to have finite order. Then its valuation has to be 0. That's sort of evident because zeta to the n equals 1 implies that n times the valuation of zeta is equal to 0, because the valuation of 1 is always 0. That is clear because V is a homomorphism from K star to R. Okay, so it takes 0 to, or rather it takes 1 to 0. So the n times V of zeta is equal to, I take the valuation on both sides of this equation. On the left, I'll get n times the valuation of zeta. On the right, I get 0. So this implies that V of zeta itself is 0. In particular, if I look at the element -1, it's a torsion element because -1 squared is 1. So its valuation has to be 0.
So,
And similarly,
so the
V of
definition
minus
means
x
that
for any x in k, V of minus x is going to be equal to V of x, because V of minus x is, you write minus x as -1 times x, and then you use multiplicativity to say that V of -1 is V of minus x, is V of -1 times, or rather plus. It transforms multiplication into addition. That's what a valuation does. So, but V of -1 is 0, and what remains is V of x. Now here is something which is absolutely, which is very useful. It says that if V of x is strictly less than V of y, then V of x plus y is actually equal to V of x. Now, of course, V of x is strictly less than V of y means that the infimum is equal to V of x. The infimum, or the smaller of these two, is V of x. That's what the hypothesis is saying. So normally the condition on a valuation is that V of x plus y is greater than the infimum of V of x comma V of y. This doesn't say that it's equal to, or it could be strict. This inequality could be strict in some cases. What we are saying here is that if these two are different, then this is actually an equality. This inequality is not strict in this case. So how do we prove this? So what the axiom is that V of x plus y is always greater than the smaller of V of x and V of y. By hypothesis, the smaller of these two is V of x. We are using the hypothesis here that V of x is strictly less than V of y. That's given to us. Now this V of x, I can cleverly write it as V of x plus y minus y. This is x. I'm adding y and subtracting y. But I again apply that axiom. So to the two terms are x plus y and minus y. So this V of x, it's really V of x. It has to be greater than the infimum of V of x plus y and V of y. What is this infimum? Can it be equal to V of y? No, it cannot be. This infimum here cannot be equal to V of y, because then V of x would be greater than V of y, which is not the case. We are told that V of x is strictly less than V of y. So this infimum here has to be equal to V of x plus y. So what have we got? We have got a chain of inequalities from V of x to V of y. No, V of x plus y to V of x plus y. So all these inequalities actually have to be equalities. So we have to have equality throughout, which is to say that V of x plus y is equal to V of x. Okay, fine. So let's take a valued field, which is just a field K with a valuation V on that field. Then we have this subset O sub V, which is the inverse image of this subset from 0 to plus infinity. So this is in fact a subring. This OV is a subring of K. Why is it a subring? So if I take two elements, I have to show that the sum and the product are in the same subset. Okay, how about the sum? These two elements are in OV. It means that V of X is positive and V of Y is positive, but V of X plus Y is greater than whatever is smaller, and whichever is smaller is positive because both of them are positive. So this means that X plus Y is an OV. Similarly, this is X times Y, right? X times Y is an OV because here it's even simpler. V of X times Y is V of X plus V of Y. And if this and this both are positive, then the sum is positive. Okay? And 1 is, of course, in this subset because V of 1 is 0. And this subset consists of things whose valuation is positive or 0. Positive for me includes 0. Positive, X is positive is equivalent to saying that X is greater than or equal to 0. And this is to say that X is strictly positive. Okay. So from a valuation on a field K, I've got a subring O sub V. It's called the ring of V integers of K. And I've already mentioned that V of K star, which is a subgroup of R, is called the value group of the valuation V. Okay, so from KV, we have got O sub V, which is a subring, and V of K star, which is a subgroup. So we got these two things. Okay. Now, when is the valuation trivial? It's trivial precisely when this ring of V integers is equal to K. That's easy. I mean, if V is trivial, then clearly everything is, of course, so then the only valuations V of X is either equal to 0 if X is non-zero and it's plus infinity if X is equal to 0. So it's always positive, and if this is the trivial valuation, right? So if V is trivial, then clearly OV is equal to K. Let's prove it in the other direction. So suppose that OV is equal to K, and we want to show that V is trivial. So we'll prove it by contradiction, for which we suppose that there's some element X in K, some X in K, such that V of X is different from 0 and plus infinity. That's what it means for V to be non-trivial or essential. Then X cannot be 0 because the only element which has valuation plus infinity, X cannot be 0 because its valuation is not plus infinity, right? So either the valuation of X is strictly less than 0, or the valuation of its inverse is strictly less than 0. The valuation of X inverse is minus of V of X. So this is some real number, V of X is some real number. Either it's strictly negative, or it's if this one is strictly positive, then this one is going to be strictly negative. And therefore, I found one element which is not in K, and therefore OV is not equal to K. So this is a trivial kind of observation. If the valuation ring, this is called the valuation ring, right? Subring is It's called the valuation ring, or the ring of V integers. Here is the thing which makes it a valuation ring. The assertion is that for every non-zero x in K, either x is in the valuation ring or its inverse is in the valuation ring. This is, in fact, the more or less the defining property of what a valuation ring is. It's a subring of a field such that every non-zero element is either in the ring or its inverse is in the ring. Fine. So these properties are obvious. Now, to the ring, so to V, we have attached OV, which is a subring of K. And now we are going to say that it has a unique maximal ideal PV. So PV is defined as, just first as a set, it's defined as the inverse image of the strictly positive reals. So with V inverse of 0 plus infinity, but 0 is excluded. So you want to show that it is, first of all, an ideal, then it's a maximal ideal, and then thirdly, that it's the unique maximal ideal of OV. Okay, that it's an ideal is clear, because if, so for an ideal, what do we have? What do I have to show? I have to show that if X is in this PV and A is in OV, then AX is in PV. But this is absolutely clear, because X is in PV means that the valuation of X is strictly positive. A is in OV means that the valuation of A is positive. Now the valuation of AX is the valuation of A plus the valuation of X. This is strictly positive and this is positive. So the sum of these two things has to be strictly positive. And therefore AX is in this PV, and therefore PV is an ideal, right? Okay, so it's an ideal. Now I want to show that if there is a maximal ideal, so which will follow from the fact that if I have an element of the ring which is not in this ideal, then it's actually invertible. Okay, that's enough to show that it's a maximal ideal. So how do I show that it's invertible? If it's in the ring but not in this ideal, it means that its valuation is 0. And therefore the valuation of its inverse is also 0. This inverse is being taken in K star, right? But if its valuation is 0, then this inverse has to be in OV, because OV consists of all those elements of K whose valuation is positive. Now, if X inverse is in OV, then X is in OV star. That's what it means for X to be in OV star, right? Its inverse should be in OV as well. So this is easy, that it's a maximal ideal. So when I take the quotient of OV by PV, I get a field. And that field is called the residue field of the valuation V, or of the ring OV. And sometimes of the field, of the valued field KV, right? Sometimes it's also called the residue field of K. Of course, it's not a quotient of K, it's a quotient of the ring OV, but sometimes you do not adhere to absolutely correct terminology. So this is called the residue field. elements of this group OV star are called V units. We have been calling elements of ZP star, we have been calling them units, right? And this is the general situation. Okay, so we could give this example here. If K is equal to QP and V is equal to what we had called VP, then this OV is equal to ZP, and what else? Then K and KV, or this PV is equal to P times ZP, and this little kV is equal to FP. This is easy to verify. So more or less by definition, this sequence is exact. K star to VK star, it's a homomorphism. It's surjective by definition because we are just taking the image of K star under V, and by definition, the kernel of this is this is not by definition, but we have shown that the kernel of this map V here is actually OV star. Kernel of V is OV star, right? Because if V of x is 0, then V of x inverse is also 0. So V of x inverse belongs to OV, so x belongs to OV star. And conversely, if y belongs to OV star, then y times y inverse is equal to 1. These are elements of OV, right? And so what do I want to show? I want to show that that V of y is equal to 0. That's true because V of y is at least positive. So is V of y inverse. And there are these two positive things whose sum is 0, because V of y inverse, which is equal to V of y plus V of y inverse on the one hand, but y inverse is 1, so V of 1 is, and V of 1 is 0. So V of y plus V of y inverse, these are two positive numbers whose sum is 0, so both of them have to be 0, and that shows that the units are contained. That shows that OV star is contained in the kernel of V. That the kernel of V is contained in OV star. We have shown it here earlier, and therefore we have both the inclusions, and therefore you get this equality. And that's why you have exactness of the sequence here. Or yeah, here. The kernel of V is equal to the image of OV star. Okay. Okay. Now, of course, this map from OV to KV is surjective. But that does not mean that the map from OV star to KV star is automatically surjective. That's not true. For example, I mean, not true in general. In this case, it's going to be true, and we are going to prove it. But in general, for example, the map from Z to Z mod 5Z, this is surjective, of course. And but the map from Z to the map from Z star to Z mod 5Z star is not surjective, right? Because this is just plus minus 1, and this consists of plus minus 1 and plus minus 2, perhaps, right? So that this consists of 4 elements here. Anyway, so that's a generality. In general, this map is not surjective, but in this case, OV star to KV star is surjective. How do you prove this? So let's take an element in OV star. To say that its image in KV is in KV star is the same as saying that X is not in PV, but X not in PV means that X is in OV star. Okay, and therefore this map is surjective. I mean, we have already proved that if every element of OV which is not in PV is in OV star. Okay. So we have proved that this here is surjective, and the kernel by definition is U1. U1 is the kernel of this map. So it can also be written as 1 plus PV, because PV, of course, is the kernel of the map from OV to KV. KV, because KV is OV modulo PV. So the kernel is exactly PV. And this U1 is the, if I call this map pi, then U1 is the inverse image of 1. Okay, the element 1 in KV. This element is the element 1 in KV. And so sometimes 1 is, of course, the image of, no, what is it called? Pi of 1 plus PV. So sometimes you write U1 as 1 plus PV. Okay. Okay. So we come to the notion of the equivalence of two valuations on the same field K. So suppose we have two valuations V1 and V2 on the same field K. We'll say that they are equivalent, and we denote it by this tilde, if V1 is C times V2 for some real number C, strictly positive real C. Okay, so that's the definition. And the first observation is that if V1 and V2 are equivalent, then their valuation rings are the same, and the maximal ideals of those two valuation rings are also the same. Okay, so this should be more or less absolutely obvious, because a number is positive if and only if, when I multiply it by a strictly positive real number, it is positive. So multiplication by strictly positive real numbers doesn't change the fact that a number is positive or not negative, right? So, and the next thing is that if a valuation is essential, not trivial, and discrete, then there's a unique normalized valuation which is equivalent. There's a unique normalized discrete valuation equivalent to it, right? This sentence is not complete. Equivalent to it, because you have the value group is going to be multiples of some strictly positive real number A, and if I replace V by what is it, A inverse times V, then the value group is going to be what? 0, 1, 2, minus 1, minus 2. So this is the one which is normalized, right? And obtained from this V, which by multiplication by a strictly positive real number. Okay. So that's the notion of the equivalence of two valuations. Now we have this proposition. Before I state and prove it, I'd like to see if there are any questions. Okay, so there are no questions. Fine, let's continue. Now, the proposition says that if I valued field k comma v, then these two conditions are equivalent. What? The first one is that the valuation, this maximal ideal of the valuation in PV, which we have defined, right? That it's a principal ideal generated. Principal, of course, means that it can be generated by a single element. So that's the first condition, that PV is a principal ideal. And the second condition is that the value group is a discrete subgroup of R. Okay. So the value group is a subgroup of R. It could be discrete, it could not, it may fail to be discrete. And the ideal PV is principal precisely when this subgroup is discrete. Okay, now the implication 1 implies 2. We may assume that this PV has some generator pi. Then, of course, this pi generates the group Vk star. This should be more or less obvious. Okay. Let's prove the converse. So for the converse, if V is, what we have to show is that if the value group is a discrete subgroup, then the ideal is principal. Now, if there's one case which is easy. If V is trivial, then of course the value group is the trivial subgroup, and P of V consists of just the zero element, because zero is the only element whose valuation is positive there, plus because it's plus infinity. And therefore, this is just a principal ideal. There's no problem. So if the valuation V is not trivial, but it's of course discrete by hypothesis, then it has a uniformizer. This is what does uniformizer mean? Pi is by definition, pi is a generator of the value group of V, K star. Pi is a positive generator of this as a subgroup of R, right? Okay, so I claim that the principal ideal, the ideal PV is a principal ideal and in fact generated by any uniformizer pi. So one inclusion is absolutely clear, that pi, the ideal generated by pi, is contained in PV. Conversely, if I take an element x in PV, I have to show that it's a multiple of pi. Then V of x, what I know is that V of x is a multiple of V of pi, right? Because V of pi generates. Oh, wait a minute. I shouldn't have said here. I should have said pi is a generator, positive generator of V of k star. No, V of pi is a positive generator of k star. So V of pi, so if I take an element, non-zero element in PV, then V of x is a positive multiple of V of pi. Now I look at x pi inverse to the power n. Let's call it a. What's the valuation? Its valuation is 0. Because V of a is equal to 0. V of a is equal to V of x minus n times V of pi, but V of x is equal to n times V of pi, so it's 0, right? So it's a unit, And therefore, x is equal to a times pi to the n. And therefore, PV is containing the ideal generated by pi. This is completely elementary, so you can just verify it for yourself. So here comes another proposition. You take a valued field kV, so K is a field, V is a valuation on K, and you take the ring of V integers, OV, and take the unique maximal ideal of OV, PV. Okay. And the assertion is that if this PV is principal, and we know that it's principal if V is discrete, right? But here it says that if PV is principal, then in fact the only ideals of OV are, of course, the zero ideal and powers of this principal ideal PV. How do you prove this? Now, if the valuation V is trivial, there's nothing to prove because in fact the ideal, because in that case PV is equal to the zero ideal and the only ideal, and OV is actually equal to K. So K doesn't have any ideals apart from this ideal, of course, and the whole of K, right? But that whole of K is maybe equal to PV to the power 0. That's why I allow n to be 0 when PV, for any ideal, if A is an ideal in some ring R, then A to the power 0 is of course equal to R, right? Anyway, so let's come back to the proof of this. I have to show that the only ideals are the zero ideal and the ideal, the powers of PV. If the valuation V is trivial, then there's nothing to prove. So we may assume that V of K star is equal to Z. Why may we assume this? Because we have, we know that if PV is principal, then the valuation V is discrete, and every discrete valuation is equivalent to a unique normalized discrete valuation. And when I change one valuation to an equivalent one, I don't change the ring of integers, nor do I change the maximal ideal in that ring of integers. Okay, so I can assume that V of K star, the value group, is equal to Z. So take any non-zero ideal, and then the image of the non-zero elements of that ideal is by definition a subset of n. But any subset of n which is not empty has a smallest element. Okay. So that smallest element is V of A for some A in the ideal A. Then we are going to prove that this ideal A is generated by this element A. And it's also equal to, it's also generated by pi to the power V of A. Okay, so take an element B in A, then V of B is greater than V of A by the definition of this A. So V of BA inverse is positive, which means that BA inverse is in the ring. Let's call it X, this BA inverse. Then B is a multiple of A. So B belongs to the ideal generated by A. In other words, A is generated by this by the element A. The ideal is generated by A. And similarly, I mean, it's exactly the same kind of argument, which shows that it's also generated by pi to the power V of A. Because what is the valuation of A times pi to the power minus V of A? Let's call it Y, this element. Then it's the valuation of A minus the valuation, the valuation of A from here, and minus the valuation of A times the valuation of pi, I should have written, but the valuation of pi is equal to 1. So it's not there, and therefore this difference is 0, and therefore A is y times this. In other words, A is a multiple. A and this pi to the power v of A differ by a unit, and therefore they generate the same ideal. Okay. Now, you see, we have been looking at, we have been using the notion of valuations. There's a related notion called that of norms. They are related because you have the group R, additive group, and you have the multiplicative group R star plus. This is a multiplicative group. And you have actually an isomorphism e to the, for some reason I want to call it e to the minus x. So this is an isomorphism from R to R star plus. And this reverses the order. Both of them are ordered groups. This and this, they are both ordered groups. They are isomorphic as groups, but this map, the exponential map, but with a minus sign here, is an isomorphism which reverses the orders. So this is the group R. Just as you had this R union plus infinity, here the analog is going to be R star plus union 0. To this additive group, I'd adjoin this element plus infinity. To this multiplicative group, I'll adjoin the element 0. So that's what I get, 0 to plus infinity. This is an ordered multiplicative monoid. It's isomorphic to R union plus infinity, as I've just explained. Here is the isomorphism. This goes to e to the power minus x if x is different from plus infinity, and goes to 0 if x is equal to plus infinity. And if x is less than y in this R union plus infinity, then of course e to the minus x is greater than e to the minus y. Okay, so this is to motivate the definition of a norm on a field. It's a homomorphism denoted like this, like the absolute value sign from the field K to this 0 plus infinity, which is a morphism of multiplicative monoids. So this just means that it takes products to products here. It takes 0 to 0. But the important property is that the sum, the norm or the absolute value of x plus y is always less than the absolute value of x plus the absolute value of y. So this is not your usual absolute value on the real numbers or complex numbers. Here the field K is completely arbitrary, and that's why this is also being called norm. So a norm or an absolute value, it's not the absolute, it's also called an absolute value. So it's just a map from K to 0 to infinity to the positive reals. Yeah, positive reals is what this set is, such that which is multiplicative, takes 0 to 0, and under addition, the norm of x plus y is less than the sum of the norms of x and y. That's, of course, the triangle inequality. So a normed field is just a field with a norm, just as a valued field is a field with a valuation. And of course, the trivial norm is the one in which everything has norm 1 except 0, which is norm 0. Right? and I'll call it essential otherwise. And here is an important distinction between un-Archimedean and Archimedean norms. So it's called, this normed field is going to be called un-Archimedean if the norm of x plus y is less than not just the sum of these two, but it's smaller than whichever is bigger among these two. So this is somehow reminiscent of v of x plus y is greater than inf v of x, v of y. It reminds you of this, right? Except that the order has been reversed. So here it was greater than, here it's less than, and here it's inf, and here it's sup. But that's exactly what's going on, because this e to the minus x reverses the order. Anyway, so I've already explained that if I have a valuation on k, then I get an un-Archimedean norm on k by sending v to e to the minus v. If the valuation is x going to v of x, the corresponding norm is x going to e to the minus v of x. And similarly, if I have a norm on a field which is un-Archimedean, it doesn't work for an Archimedean norm. So if I have a norm which is un-Archimedean, then so the norm is x going to mod x, right? Then x going to minus log mod x is a valuation on k. So the idea is that this is actually a bijection between valuations on k and un-Archimedean norms. Okay. So another observation is that if I have an element of finite order, then its norm is equal to 1. By the way, this norm should not be confused with the norm map from, let's say, C to R, from C star, or from C to R, the norm map. Or, you know, if you have an extension of fields L over K, let's say it's a finite extension, then you have a norm map, norm L over K from L to K. This norm is not to be confused. I mean, this is a totally different concept of a norm. Unfortunately, you use the same word to denote these two very different notions. Okay, so if psi is an element of finite order, then its norm is 1. And so, for example, every finite field, then there's no norm, only the trivial norm is there, because every element in, for example, every element in FP star has finite order, right? Okay. And here's the proof. If psi is killed by n, then norm of psi to the power n is equal to 1. And the only element in R star, strictly positive, which has the only x such that x to the n is equal to 1 is x equal to 1 itself. Okay. So as a corollary, the absolute value of -1 has to be 1, and the absolute value of minus x has to be the same as the absolute value of x. So I'll interchangeably call it the norm or the absolute value. Now, two norms on the same field K are said to be equivalent, and this is the notation, if one is obtained from the other by raising to some power for some strictly positive real gamma. So obviously this is an equivalence relation, and it's an equivalence relation which preserves the property of being trivial or being Archimedean. And you know, these Archimedean norms correspond to valuations, and we have a notion of equivalence of valuations and the notion of equivalence of norms. So what this is saying is that these two coincide under this assumption. So another way of saying the same thing is that if you have, what is it, valuations here, and we have given a bijection with an Archimedean norms, that's one thing. Then you have a notion of equivalence here, so you can pass to the equivalence classes. You have a notion of equivalence here as well, so you can pass to the equivalence classes here as well. And what this is saying is that this bijection gives rise to this bijection, as to a bijection here. Okay, so now the proposition says that two essential norms on the same field K are equivalent if and only if this condition in the first norm implies the same condition in the second norm for every x in our field K. Now, if the norms are equivalent, then clearly you have this, because you just apply the definition of equivalence of norms, right? Now, conversely, let's fix an A in the field such that whose norm is strictly less than 1. Whose first norm, norm 1. I can do that because these are essential norms. None of them is trivial. Of course, we have excluded the trivial norms. So what do we have by hypothesis? A2, the second norm of A is also strictly less than 1 by hypothesis, because norm x, norm 1 less than 1 implies norm 2 strictly less than 1, right? This is what this is the hypothesis now. What we have to show is that this is equivalent to that. Of course, this holds for all x in K. That's what we are proving. We are proving this implication. And so we have to produce somehow a gamma such that this is equal to the second norm to the power gamma or something. For all x, we have to prove it for all x in K. But if we fix one element A, then obviously there is a gamma, right? This is because we have two elements. This is strictly less than 1. This is strictly less than 1. So one is a power of the other. I mean, if you have any two elements, A and B, then of course I can write A as B to the power gamma for some gamma, which is strictly positive, right? So that's what I've done. I've fixed an element A, and for that I've defined the gamma. Now we will prove that the same gamma works not just for this A, but it's not A2 here. The 2 is here. It works not only for this A, but it works for any x, and that will show that these two norms are equivalent. Okay, so take an x in K star such that the norm of x is strictly less than 1, then of course there is an alpha such that norm of x. So just as I explained here, you define this alpha by this requirement, because the norm of x is less than 1 and the norm of a is also less than 1, right? Now, if I take two integers which are strictly positive, such that this a is not a here, it has to be alpha, such that this alpha here, the exponent, is less than, strictly less than m over n. Alpha is a real number, but I can find a rational number m over n, such which is strictly bigger than this alpha. Then what do we have? Then from this equality and this inequality, I get this inequality. And which is equivalent to saying that I have this. Okay. Now, my hypothesis is that if this is less than 1, then this is also less than 1. Now I'm taking y to be this element here. And I've got this, so I get this. And therefore I get this. Okay. Now you repeat the argument with some rational number m over n, which is strictly less than alpha. Here I had taken a real number, a rational number m over n, which is strictly bigger than alpha. And now I take some m over n, which is strictly less than alpha. And I repeat the same argument, and I'll get a similar conclusion. This sort of thing will get reversed here, because I've reversed the inequality here. Okay. Now you take a sequence of rational numbers tending to alpha. And by this will imply that norm 2 of x is exactly norm 2 of k to the power alpha. Okay. But then what do we have? x1, so this is what, this is for all x in k. And so this is what we had started with. And anyway, so we get the equivalence of these two norms. I mean, this is just what follows from all this that we have done, right? Okay. So now if I have, the corollary is that if I have two essential valuations on the same field k, then they're equivalent if and only if these maximal ideals, there's an inclusion of these ideals. Okay. So by the way, you cannot simply say that, oh, both of them are maximal ideals, but one is containing the other, so they have to be equal. No, but this is in OV1, and this is in OV2. So a priori, they are not even ideals in these rings may be different a priori. So anyway, we have to prove that if the valuations are equivalent, then there's this, they're equivalent if and only if there's this inclusion of these ideals. So you go from these valuations to these norms, and then the ideals just which consist of elements with strictly positive valuation will, so the translation is that they consist of elements x and k whose norm is strictly less than, well, this should be 1 here, strictly less than 1. Okay, so the inclusion is equivalent to these two norms being the same, being equivalent, and the norms being equivalent is the same as the valuations being equivalent. Okay. Now we have this notion of distance associated to a norm. So if I have a norm on this field K, then I define the distance of X and Y to be just the norm of X minus Y. And it's clearly a distance because there are 3 conditions which one is to check. 1, 2, 3. The first one is that the distance from X to Y is equal to 0 if and only if X is equal to Y. But that's true because the distance is 0 is the same as saying that the absolute value or the norm of X minus Y is 0. And we know that that happens only when X minus Y itself is 0, which is the same as saying that X is equal to Y. And then you have to show symmetry. So distance between X and Y is the norm of X minus Y. But that's the same as the norm of Y minus X, because the norm of minus 1 is 1. And norms are multiplicative, etc. So that's the distance from Y to X. But the important thing is this triangle inequality. The distance from X to Z should be less than the sum of the distances from X to Y and Y to Z. How does that follow? By definition, the distance between X to Y is the norm of X minus. X to Z is the norm of X minus Z. But I can write X minus Z as X minus Y plus Y minus Z. So one of the conditions for being a norm is that this thing, which is the sum of these 2 terms, the norm has to be less than the sum of the norms of these 2 terms, and that is the distance from X to Y and the distance from Y to Z, right? Okay, so from a valuation you get a norm, from a norm you get a distance, from a distance you get a topology. That is what, I hope you are familiar with this, how a distance gives rise to a topology on a set. And the topology is discrete if and only if this norm is trivial. So one of the implications is obvious, and the other is proved by contradiction. So I'm proving this implication, which means that I'm assuming that the topology is discrete, and I have to show that the norm is trivial. By reductio ad absurdum, I can assume that the norm is not trivial, that it is essential. Then what does it mean for it to be essential? It means that there is an element X in K star such that its norm is strictly between 0 and 1. So the sequence X to the power n will tend to 0 as n tends to plus infinity, which means that the topology is not discrete. Because in a discrete topology, a sequence tends to something if and only if it's eventually stationary, right? Stationary means it's a sequence, I mean, it goes on, but eventually it's the same term being repeated. Otherwise, it doesn't even converge. Okay. So if K is complete for a valuation or a norm, if it is complete for the corresponding distance, that's a definition. Complete for a distance, you know that it means that every Cauchy sequence converges. That's what it means for it to be complete for a distance, right? So the proposition is that if I have 2 norms on the same field, they are equivalent if and only if they define the same topology on K. So remember, I'd said if you have a norm, it gives rise to a distance, and the distance gives rise to a topology. Can it happen that you have two norms? I mean, it can happen that two norms give rise to the same topology, but that can happen only if the two norms are equivalent. That is what this proposition is saying, and that's what we have to prove. So if they are equivalent, then of course they define the same topology. Conversely, if the topologies are discrete, then of course the norms have to be the trivial ones. So there's nothing to prove there either. Now, so we may assume that the topology is not discrete. And we have to prove that so we will prove it by contradiction. So if the norms are not equivalent, then the topologies are different. Let's call them T1 and T2, the topologies corresponding to the first norm and the second norm. So if the norms are not equivalent, what does it mean? It means that there's an element x in K such that, what is it? There should be a 1 here and a 2 here. There's an element x in K such that the first norm is less than 1 and the second norm is greater than, strictly less than 1 here and greater than 1 here. That's what we have proved earlier, that if this less than 1 implies, then this implies that these two norms are equivalent. We have proved this earlier. So if they're not equivalent, it means that there's some element x such that the first norm is strictly less than 1 and the second norm is greater than 1. And what does that mean? That means that if I look at the sequence x to the power n, consisting of powers of this x, then it tends to 0 in the first topology, but not in the second topology, which means that the topologies cannot be the same. If there is some sequence which converges in the first topology, but not in the second, then the topologies cannot be the same. Okay, so now here is something which is somewhat peculiar for these valued fields. Valued fields are the one which correspond to un-Archimedean norms, right? So the unusual thing is that a series converges if the general term tends to 0. That is an unusual thing. If it converges, then the general term tends to 0 is the usual thing. That's what we are familiar with in the everyday real and complex topologies. But here, the converse is also true. If the general term tends to 0, then the series converges. Now, that's peculiar, so let's look at this. Let's call SR the Rth partial sum. And suppose first that this series converges to some S. Then what is the limit of XR as R tends to plus infinity? Is the XR is SR plus 1 minus SR, because SR is this partial sum. So the limit of a difference is the difference of the limits. So you have the first limit and the second limit, but of course they are the same limit. So the limit of XR is equal to 0. This, we have not used the fact that that we are in an un-Archimedean situation. So this is true in general. The converse is, you will see that we have to use some un-Archimedean arguments. So suppose that the general term tends to 0, which is the same as saying that the valuation tends to plus infinity, as n tends to infinity. Okay, this means that for every real number epsilon, however large it may be, epsilon people usually take it to be a small number. I'm taking it to be, it's in your interest to take it to be a very large number. Anyway, so for every epsilon, which is however large it may be, you can always find some index n epsilon, such that whenever little n is bigger than n epsilon, then v of xn is strictly greater than epsilon. That's because these vn's are tending to plus infinity, right? Vxn's are tending to plus infinity with n. Now for every m, what is v of Sn plus m minus Sn? Sn plus n m minus Sn, it consists of, it's equal to xn plus 1 plus xn plus 2 plus xn plus m. This is Sn plus m minus Sn. That's what it is equal to. And the valuation of a sum is always bigger than the smallest of the valuations of the summands. But because of these, because my n is such that it's greater than n epsilon, I will have all of these. So the infimum has to be at least epsilon. This means that the sequence SR is quotient. And because K is complete, it converges. Okay? So this is, I mean, it has been crucially used that the sum, the valuation of a sum is bigger than the infimum of the valuations of the terms. Okay, I have a little time, so I can maybe try to do this one here. Yeah. So let's start with the field K with a valuation V on it. Then, of course, you have the ring of V integers and the unique maximal ideal PV of that ring OV. And you can form these quotients OV modulo PV to the n, and you can take the inverse limit of these quotients. Let's call it AV. And of course, by the very construction, you have a homomorphism of rings iota from OV to AV, just as you have a map from Z to ZP, because this is the inverse limit of over n of Z mod P to the n. Similarly, if I have any ring O and an ideal P, then, or I mean, well, yeah, so you get this map iota, right? The proposition is that suppose that V is discrete and this field K is complete, then this iota is actually an isomorphism. In general, of course, it's not an isomorphism. This map from Z to ZP is not an isomorphism. But the hypothesis is that V is a discrete valuation and the field K is complete for the corresponding distance. Then this iota is an isomorphism. So you can see that there's nothing to prove if V is trivial. So we may assume that V is essential, and then let's prove that I is injective, iota is injective. So what does it mean to say that iota of x is 0? It means that that x is in PV to the n for all n. But that implies that x is 0 because the intersection over n of PV to the n is 0. Okay. Now let's show that it's surjective. So you take an element in AV, and every element in AV is a sequence like this, where AN is an OV modulo PV to the power n, and AN plus 1 is congruent to AN modulo PV to the power n, right? Exactly as in ZP that we have been looking at earlier. So these ANs are in these quotient rings, but I can always find elements of OV which lift these ANs. So let Xn lift AN, and then I get a sequence Xn in the ring O. So, or let's first consider it in the field K, and the claim is that it's a quotient sequence. How do you establish this claim? So I have to, let's look at xn prime minus xn for n and n prime, which are greater than some fixed n. Fix an n, and take any two indices n and n prime, which are both greater than this capital N, then xn prime is congruent to an modulo pv to the n, and xn is also congruent to an modulo pv to the n. That means that this difference is in pv to the n. So, in other words, I mean, the bigger the power here, the smaller the difference. I mean, this is exactly what is needed to show that this is a Cauchy sequence. And because the field K is complete, this sequence converges to some X in K. And in fact, this X is in OV because OV is a closed subspace of K. So the limit of any sequence of elements of OV is again in OV. Now, it just remains to check that I of X is equal to A, and this is more or less the case by construction. So we get the result that iota is surjective. So this iota, which is a map from OV to AV, and this OV was the limit over n of OV modulo PV to the power n. So this is an isomorphism, and therefore another way of saying it is that this OV is, I mean, you just identify OV with this inverse limit. So you just say that OV is the inverse limit of this system. Yeah. Just as ZP is the inverse limit of ZP modulo P to the n ZP, the inverse limit over n. That's because so one reason is that it's by definition. But if your ZP is constructed as the ring of VP integers in QP, you first construct this QP as the completion of Q for the valuation VP. Then you define ZP as the ring of V integers to show that new definition is the same as the old definition is what this proposition is doing, right? Okay, so let me stop here today, and next time we will continue, and the norm map as defined by in the tutorial will come into play in the next lecture. So are there any questions? Yeah, there are no questions? Fine, so I'll stop here.